Welcome back, students. Our objectives for today: explain the concept of acid ionization constants and write acid ionization equilibrium expressions. Review the ionization constant of water. Explain buffering. Compare cation and anion hydrolysis. Ionization constant of a weak acid. The term Ka is called the acid ionization constant. The acid ionization constant Ka is constant for a specified temperature, but has a new value for each new temperature. Acetic acid is a weak acid, and most of the acetic acid molecules remain unionized. An acetic solution contains CH3COOH molecules, hydronium ions, and acetate ions. The equilibrium equation for the ionization of acetic acid is as follows. The equation for Ka is as follows. And so it's just another equilibrium expression, products over reactants. And again, pure substances, well, because water is the solvent, one can assume that the molar concentration of water molecules remains constant. The concentration of water is thus not included in the equilibrium expression. So these are some Ka values. You'll notice that the Ka values are pretty close together, even though we can change the concentrations of the acetic acid quite a bit. At constant temperature, an increase in the concentration of acetate ions through the addition of sodium acetate disturbs the equilibrium. This disturbance causes a decrease in hydronium ions and an increase in acetic acid molecules. The equilibrium is reestablished with the same value of Ka, but there is a higher concentration of non-ionized acetic acid molecules and a lower concentration of hydronium ions. Changes in the hydronium ion concentration affect pH. Buffers. Buffered solutions resist changes in pH. Buffered solutions contain both a weak acid and a salt of a weak acid. For example, acetic acid and sodium acetate. Really, there shouldn't be a negative there. Well, just be aware there isn't really a negative there. Buffered solution can react with either an acid or a base. When small amounts of acids or bases are added, the pH of the solution remains nearly constant. Buffered versus non-buffered solutions. The beaker on the left contains a buffered solution and an indicator with a pH of about 5. The beaker on the right contains mostly water with trace amounts of acid and an indicator. The pH meter shows a pH of 5 for this solution. After 5 milliliters of a 0.1 molar hydrochloric acid solution is added to both beakers, the beaker on the left does not change color, indicating no substantial change in its pH. However, the beaker on the right undergoes a definite color change, and the pH meter shows a pH of 2.17. If a small amount of acid is added to the acetic acid sodium acetate solution, acetate ions react with most of the added hydronium ions to form non-ionized acetic acid molecules. The hydronium ion concentration and the pH of the solution remain practically unchanged. If a small amount of base is added, the hydroxide ions of the base react with and remove hydronium ions to form non-ionized water molecules. Acetic acid molecules then ionized and mostly replace the hydronium ions. The hydronium ion concentration and the pH of the solution remain practically unchanged. A solution of a weak base containing a salt of the base also behaves as a buffered solution. Buffer action has many important applications in chemistry and physiology. For example, human blood is naturally buffered to maintain a pH between about 7.3 and 7.5. Ionization constant of water. The self-ionization of water is an equilibrium reaction. We kind of mentioned that a little bit when we first looked at acids and bases. Equilibrium is established with a very low concentration of hydronium and hydroxide ions. Notice water doesn't have to go on the bottom because it's a pure substance, well, pure liquid. Hydrolysis of salts. Salts are formed during the neutralization reaction between a Bronsted acid and a Bronsted base. When a salt dissolves in water, it produces positive ions of the base from which it was formed and negative ions of the acid from which it was formed. If the ions formed are from weak acids or weak bases, they react chemically with the water molecules, and the pH of the solution will have a value other than 7. Am I little cursor is freaking out, but it's okay. A reaction between the water molecules and ions of a dissolved salt is called hydrolysis. If the anions react with water, the process is anion hydrolysis, and it results in a more basic solution. If the cations react with water molecules, the process is cation hydrolysis, and the results will be a more acidic solution. Anion hydrolysis. In a Bronsted sense, the anion of the salt is the conjugate base of the acid from which it was formed. It is also a proton acceptor. If the acid is weak, its conjugate base, the anion, will be strong enough to remove protons from some of the water molecules. An equilibrium is established in which the net effect of the anion hydrolysis is an increase in the hydroxide ion concentration of the solution. The equilibrium equation for a typical weak acid in water, HA, is as follows. A just represents the anion component, yada yada. The general equilibrium equation is yada yada. The hydrolysis reaction between water and the anion, A to the negative, that is produced by the dissociation of the weak acid, HA, is as follows. The extent of hydroxide ion formation and the position of the equilibrium depends on the relative strength of the anion. The lower the Ka value of HA, the weaker the acid, HA, the stronger its conjugate base, A to the negative, will be. Aqueous solutions of sodium carbonate are strongly basic. The carbonate ions react as a Bronsted base. The hydroxide ion concentration increases until equilibrium is established. So let's take a look at cation hydrolysis. In the Bronsted sense, the cation of the salt is the conjugate acid of the base from which it was formed. If the base is weak, the cation is an acid strong enough to donate a proton to a water molecule to form hydronium ions. The net effect of the cation hydrolysis is an increase in the hydronium ion concentration of the solution. The equilibrium equation for a typical weak base, B, is as follows. Thus the Kb, for the base dissociation constant, is as follows there. I noticed when I imported these into my slideshow software that some of the negatives and some of the positives got switched to this strange little G symbol. Most of those I caught and fixed. That one I did not. The hydrolysis reaction between water and the cation BH positive, produced by the dissociation of the weak base B, is as follows. The extent of the hydronium ion formation and the position of the equilibrium depend on the relative strength of the cation. The lower the Kb value of B, the weaker the base, and thus the stronger its conjugate acid will be. Hydrolysis is in acid-base reactions. Hydrolysis can help explain why the endpoint of a neutralization reaction can occur at a pH other than 7. Salts can be placed in 4 general categories depending on their hydrolysis properties. Strong acid, strong base, strong acid, weak base, weak acid, strong base, weak acid, weak base. Salts of strong acids and strong bases produce neutral solutions. Neither the cation of the strong base nor the anion of the strong acid hydrolyzes appreciably in aqueous solutions. The aqueous solutions of salts formed from reactions between weak acids and strong bases are basic. Anions of the dissolved salt are hydrolyzed by water molecules, and the hydroxide ion concentration increases. This raises the pH of the solution. So we have a little example illustration there. Salts of strong acids with weak bases produce acidic... Let me start that one over again. Salts of strong acids and weak bases produce acidic aqueous solutions. Cations of the dissolved salts are hydrolyzed in the water solvent, and hydronium ion concentration increases. The pH of the solution is lowered. Salts of weak acids and weak bases can produce either acidic, neutral, or basic aqueous solutions depending on the salt dissolved. Both ions of the dissolved salts are hydrolyzed extensively, and so here we have another little depiction of that. Equilibrium and pH calculations, and so this just sort of gives us a general overview of all of the calculations involving pH. If we have something that's nice and strong, we can go straight to our logarithm function. If we have something weak, we're going to have to take into account the Ka value or the Kb value if we're looking at a base. So we solve them essentially the same way: weak acids and weak bases, strong acids and strong bases. Alright, well that does conclude this section, so please write down any questions you have. There's a lot of material in there, so you should have a few questions. I look forward to seeing you in class soon. Bye!